Okay, so when we hear the terms work, energy, and power, what are we thinking? So what do you think about when you hear work? Energy expended, yeah, so we're going to definitely have some relationship between our work and energy. What quantities do we think are going to be involved in a measure of work? Time, okay, so we could look at time in a special way. Force. Force is going to be the big one, right? So when we're looking at force, right, we're going to be able to look at how much force we exerted, right, over a certain distance. And we'll sort of start linking these back to our Newtonian mechanics. So the nice thing about your work, energy, and power stuff, particularly when we're getting into the concept of work, is it's going to be very related to when we talked about Newtonian mechanics. So for Newtonian mechanics, we had the concept of impulse. And what was an impulse? Yeah, how much force we exert over a certain amount of time. Well, when we get into work, it's really similar. Now it's how much force we exert over a certain displacement. So work is force times displacement. So if we think about applying a force to this table for some displacement, I have done work, okay? Now, if I apply more force, I'll do more work. If I apply the same force over a larger displacement, I'll do more work. And when we link that back to Newtonian mechanics, if I'm pushing on this for a larger displacement or a longer distance, what is that going to do in terms of the time I'm applying forces for? Yeah, it's going to be more. So if I apply the same force for a longer displacement, I'm also going to be applying that force for a longer period of time. So we're quickly going to be able to start making relationships between our Newtonian kinetics and our discussion of work. Now, when we try to apply a force to an object and we move that object, our force is going to be measured in newtons and our displacement is going to be measured in meters. So the units for work are going to be the Newton meter. And you've probably also heard the term joule when we start linking work to energy. So 1 Newton meter is equivalent to 1 joule. So when we look at doing this then, we need to have some convention on the direction of work. So first of all, we can look at pressing a bar up. So if I press a bar up, we can call that positive work, okay? And we'll talk about why we would classify that as positive work in a second here. If I then lowered the bar down, we'd have that be negative work. So if I press the bar up and lower it back down, or I start at the top, come back down, and press back to the top, how much work did I do? So coming from here, down, and back up, how much work did I do in that? I did 0 work, right? So I did 0 mechanical work, meaning that my displacement was 0. Now, who here thinks that we've done some work in that process? Okay, if you ever lifted a bar, you've probably realized it's a lot of work, right? So we've done some positive work, and we've done, or in this case, in the direction, we've done some negative work, followed by some positive work to a net 0 mechanical work. So where did the work actually happen? If we didn't do any mechanical work, but we know that we expended energy, meaning we've done some work, what type of work did we do? Physiological work, exactly, right? We've used chemistry, so we've done some chemical work. So our physiological work is just basically using which molecules to create energy. Right, we're going to use glucose, we're going to break it down, we're going to make some ATP. So we've used ATP to do work, right? We've used the energy stored in ATP to do some work inside the body. And where does that work actually occur? Yeah, at the muscle between the actin and myosin, right? Your myosin heads are going to grab on and they're going to go boop. So your myosin heads had some displacement. That displacement is work. So we've used energy in the form of chemical energy to do physiological work. So even though we didn't accomplish anything in terms of mechanical work, because the bar ended where it started, we did a substantial amount of work to get there. Now, getting back to this concept of positive versus negative work, if we know that we've done no mechanical work, often what we'll want to do is keep track of absolute work. So absolute work means we're taking into account the positive and negative work done, and we just take that negative work and we take the absolute value, because Everybody knows doing eccentric work is just as important as doing concentric work, and in some cases more important, right? So if we're looking at that eccentric loading, if we still value that eccentric loading as a component of training, that's still work we want to keep track of. And so what we can do is we can take account of the absolute work done. So rather than saying we started here and we finished here, so we did no work, we actually did twice as much work because we have our negative eccentric work and our positive concentric work. So that gets into our classification of how we deal with work in the human body. We tend to classify it as positive work being a concentric load. And when we talk concentric, what do we mean? What is a concentric contraction? Yeah, active shortening of the muscle. Okay? Whereas our eccentric is lengthening, but more specifically, yeah, active resistance of lengthening. Okay? So concentric, active shortening, eccentric, actively resisting, lengthening the muscle. So concentric work we classify as positive work, eccentric work we classify as negative work. Let's link things back to energy. So when you think energy, what pops into your head? The sun, okay, that's an option. The sun definitely is our primary source of energy. Electricity, yeah, so our energy delivery is primarily done through the delivery of electrical power here. What about for humans? Carbohydrates, okay? Carbohydrates, great source of energy. So when we think humans, we often probably think of energy in terms of either how we're feeling, right? I'm feeling like I have lots of energy today, or I don't have lots of energy today. Or we think about it in terms of fueling, how much food we've had. But we're going to take that and we're going to look at it in terms of physics, because we love physics. Okay, so there's going to be different types of energy we can deal with. The ones that we're probably familiar with, heat, light, sound, chemical, and for us, mechanical. So we're going to focus more on the mechanical side of things. Now, within our mechanical energy, we have two different types. We have kinetic energy and we have potential energy. So looking at those terms, what do we think of when we think kinetic energy? Yeah, energy of movement. Okay, and what about potential energy? Okay, has the chance to become energy. Yeah, so the energy has some potential. Okay. If I were to knock my cup off of here, what would happen? Yeah, it's going to fall. Okay. If I were to knock my cup off of the Empire State Building versus this table, who would volunteer to sit under the cup from under the table? Yeah, it's not going to hurt. What about the Empire State Building? Probably not. Why not? Yeah, it started with more potential energy. So that potential energy is just the capacity of the object to gain kinetic energy. So if I drop it off the Empire State Building, it starts with lots of potential energy, and as it comes down, it loses that potential energy and it's going to gain some kinetic energy. So what we're really going to be talking about with our energy lecture is the ability to transfer between states of energy. So if we look at our kinetic energy, it is just the potential for an object in movement to exert a force. So it can do work. So we think of energy as the capacity to do work. So energy and work are related. So if we said that work was our impulse component, what would energy be? So impulse was the ability to change momentum. Therefore, energy is the capacity to do work, or work is the ability to change energy. So those relationships are going to link together quite nicely. So if we go back to a collision, okay, so we have two objects colliding together, okay? If those are both in motion, they both have some kinetic energy. When they come in contact, they're going to transfer energy by doing work. So one object collides with the other object, it does work on that object, and then that object leaves with some kinetic energy. So the energy of this object coming in and hitting this object means that we transfer energy from this one into this one by doing work, and then that object leaves with some kinetic energy. So in order to have a change in energy, we must do work. Okay, so if I want to change the state of energy of an object, I need to do work on that object. So if we think about this capacity to do work, if I have a faster moving object, what is that going to do for its capacity to do work? Yeah, it's going to have a greater capacity to do work than a slower moving object. Okay, what about a heavy versus a light object? Yeah, if I smack somebody with a feather, they're probably not going to be too upset about it. But a baseball bat might have some different results, right? So mass must have an effect on energy in terms of its capacity to do work. And then speed or velocity must have some effect on its ability to do work as well. And so the way we look at this is very similar to our momentum relationship, where momentum is mass times velocity. Now we're looking at kinetic energy as being half of our mass times the velocity squared. So that means that for looking at energy, the most important component is velocity. Why? Yeah, it's an exponential relationship. So our energy scales linearly with mass and exponentially with velocity. So the faster an object is going, the more energy it's going to have because of that exponential relationship. Okay, then we get into potential energy, and we're going to talk about a couple of different types. We have our gravitational potential energy, which is the example we talked about, where knock a cup off and how high it is determines how much energy it has. Why does the height give us potential energy? Gravity. Excellent. Okay? So the higher an object is, the more time gravity has to accelerate that object, right? And it accelerates uniformly at 9.81 meters per second squared. So if I have more time to accelerate that object, what will happen to the object? It'll go faster, right? Because of which relationship? More time accelerating leads to more velocity, right? We're just rearranging that equation into this. Okay, so gravitational potential energy is just the potential for gravity to do work on an object that will then cause a change in its kinetic energy. The other thing we have is strain energy. So this is the energy due to deformation. And fortunately, somebody's left me a nice flexible ruler here. So if I deform this object, what's going to happen to it when I let go? Pew, right? I've done work by deforming the object. So I have caused some deformation, and I've stored elastic potential energy. So you'll hear two terms for this, either elastic potential energy or strain potential energy, but it's energy due to deformation. That energy can then be released, causing a change in kinetic energy. So either way, our goal is to change the kinetic energy of the object. Now, looking at gravitational potential energy, it's pretty straightforward. The heavier it is, the more energy it's going to get. And then the higher it is, the more energy it's going to get, because gravity is constant. So mass times gravity times height gives us the gravitational potential energy of an object. So the higher we lift it, we get a linear scaling, and the heavier it is, we get a linear scaling. So there's no single component that determines or that has a greater impact on our gravitational potential energy. Mass times gravity times height. What about for elastic potential energy? Who here has ever pole vaulted? Okay. What characteristics of the pole affect your ability to pole vault? Exactly. So the spring coefficient of the pole, right? So how much energy it takes to deform the pole is a big contributor to how much energy we're going to get back out. And it turns out that it is not a linear relationship. So we have half of k times x squared, where k is our spring constant, meaning that scales linearly, and x squared is our deformation, meaning the more we deform it, we get an exponential increase in strain energy. So if something's really stiff, right, so it's a high spring constant, and we deform it a lot, it's going to be able to return a lot more energy. So let's bring this into a common sports example here. Okay, so if I'm going for a slap shot, what do I want to do? Do I want to just like come and smack the puck? Why not? Yeah, I want to deform the stick. So I'm actually going to hit the stick onto the ice, put some weight into that stick, flex the stick as much as I want, and I think sticks now come with like flex scores on them, don't they? Yeah, it's like flex 70 or whatever. So it's basically telling you the deformation coefficient that you get for the stick. So I hit the ice, I flex the stick, and then all I have to do at that point is I don't really have to swing forward anymore, right? With old, heavy, unflexible sticks, you kind of relied on your body's ability to swing the stick. Now, we're relying on our ability to deform the stick, and then as we release the force and carry through with the swing, what happens? The stick's going to whip out. We've stored the elastic potential energy in the stick. Then that energy gets released. That energy does work, right? So we've done work on the stick to store elastic potential energy. Then that energy that we stored, that spring or strain energy, elastic energy, is going to do work to accelerate the stick and change its kinetic energy, meaning that the head of the stick will speed up. Okay? So by deforming the stick more, we get an exponential increase in spring energy, or our strain energy. Okay? So that ability to deform the object more means we store more elastic potential energy, which can then be released to do work and create kinetic energy. So if we look at our pole vault here, the same thing happened in pole vaulting. We went from pole vaulting on wooden sticks, which kind of dangerous because they snapped, to then moving on to wooden core sticks and then fiberglass sticks, and now basically everything is carbon fiber, because the properties of carbon fiber allow for a very high spring coefficient, but also a substantial amount of deformation before it reaches that failure point. Now again, when they do reach the failure point, it is rather catastrophic and they kind of just explode, but it means that we can do more work to the pole so that we can store more elastic potential energy, so that elastic potential energy can then do work on us to lift us up off the ground. So if we think about the phases of a pole vault here, we're going to have the run-up phase. What do I do in the run-up phase? What's my goal? I need to do some work, right, to increase my kinetic energy. So I'm going to do work causing an increase in kinetic energy. Now I have some forwards kinetic energy. Now what do I need to do? I plant the pole. Yeah, I need to bend the stick. So I have to do work to the stick to store some elastic potential energy. Then what do I need to do? Yeah, I need to change my potential into kinetic and ultimately gravitational potential energy. I'm trying to increase my height. Okay, so we're going to get some kinetic energy that accelerates us upwards with the goal of increasing our gravitational potential energy. Then once I'm at the top and clearing over the pole, hopefully, right, over the bar, what happens? Now gravity's going to do some work and change my gravitational potential energy into kinetic energy, right? Now, just like when I told you about how we used to do high jump into sand pits, they also used to do pole vaults into sand pits. Why don't we want to do a pole vault into a sand pit? We're going to have a substantial amount of gravitational potential energy, which means that we'll have a substantial amount of kinetic energy. How do I stop? Well, if it took work to accelerate me, it's going to take work to stop me. So now the ground has to do work on me. If the sand doesn't have very far to displace, what has to happen to stop me? We have to increase the force, right? What does this sound like when we link back to our linear kinetics that we discussed? So if I threw a water balloon at you, what are you going to do? Besides dodge. Yeah, we want to increase the time. And we're going to take that same concept, except now instead of increasing the time that forces are applied, we're going to increase the displacement at which forces are applied. How do we accomplish that for our landing? How do we make it so that we can have more displacement in the landing? Yeah, we make it something that can compress. Like we have a big foam pad. So if we look at our big foam pad down here, that big foam pad is able to squish in a lot, and if I apply a force to deform an object, what am I going to do? Yeah, our strain or elastic potential energy. Okay, so now I'm doing work on the pad as I contact the pad. I'm going to deform the pad. Okay, so I do work on the pad to cause that conversion from kinetic energy to elastic potential energy, and the pad is doing work on me to change my kinetic energy to 0. So I'm basically turning my kinetic energy into elastic potential energy in the pad. Now, when it restores the energy back to me, when it uncompresses, that's going to happen slowly. Thankfully, the properties of foam mean that it's not going to be like boing, like a trampoline, but it's going to go squish and then slowly come back. Okay? So the key here is between all of these changes in state of energy, what had to happen? Nice and loud? Work. We had to do work. So if we want to change the state of energy of an object, the only way to do that is by doing work to that object. Now, if I do work to an object, what must be true about the relationship of work of the system of objects? Yeah, it's got to be balanced, right? So if I do work on an object, that object has to do work on me. What does that sound like? Yeah, Newton's third law, okay? So because we have a force involved, we must consider that if I exert a force on an object, that object must exert an equal and opposite force on me. If I do work to an object, that object must do an equal and opposite amount of work on me. Otherwise, we created energy out of nowhere. And as the famous saying goes, energy is neither created nor destroyed, right? So if we do work to an object, the object must do work back on us. So this is the law of conservation of energy, right? So just like we had the law of conservation of momentum. So if we have a change in state of energy, that energy will be conserved. All energy just changes state. So if we look at the example of a roller coaster, we build gravitational potential energy. Okay, so we're going to start from the top. As the roller coaster comes down that first hill, what happens? It's converted from gravitational potential to kinetic energy, right? We're going to start to go really, 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 really fast. Okay, then as I come up the first hill, what happens? Yeah, we're going to lose some kinetic energy to gain some gravitational potential energy. And so we're basically having this sliding scale where we're converting between our kinetic and gravitational potential energies. Now, is this a perfect relationship? So every little joule of energy gets converted perfectly. Yeah, we lose lots of energy to heat and sound, okay? So on a roller coaster, those tracks are going to get really hot. The wheels are going to get really hot because of friction, okay? So we have some losses of our kinetic energy to friction that creates heat. And then it's also going to create sound, lots of sound. So even though if we were to have a roller coaster roll down a hill, come up, it would never make it as high as it did before. Energy wasn't lost, it was just converted into a different state. So we went from mechanical energy into thermal energy and sound energy. Okay, so we converted it from purely mechanical energy, we added some heat and sound at the loss of some of that mechanical energy. So we'll never make it back up as high because some of that energy was converted to a different state. But it was still conserved. So even though it went to a different form, energy, the total energy of the system was still conserved because we can't create or destroy energy.